Hi, everyone, and welcome back. First of all, let me check if you can hear me. Okay, good. So there is significant latency today. It looks like about 15 seconds or so. So I will have to leave good length pauses if I ask any questions. So we have a couple of minutes before we start. Does anybody have anything they want to ask me about? No? So we'll just wait awkwardly for 3 minutes then for the official start of the class. Yes, there are a total of 4 assignments. In previous years, we've done 5 assignments. I think we'll stick with 4 this year. For assignment 1, you keep getting exceptions on question 6 and question 9. Question 6, I think, is one of the ones that has a memory limit. So that's either the 4,000 or 5,000 lines. So if you're taking all of the input and reading it into some data structure like a list, then it will fail on the larger tests because you'll exceed the memory limit. Question 9, I'm not sure. You'd have to look at a little more detail. Okay, Jackson says, I was submitting to the server perfectly fine, and then some of my tests started to have compilation errors. No idea. Is anyone else experiencing that? Yeah, so it would be strange if you submitted exactly the same thing and started getting compilation errors, unless something has happened on the server, like a disk became full or something. I can try submitting the sample solutions at the end of this class and see if it still accepts them or if there's some bigger problem. Other possibilities are you uploaded the file that you thought was the right zip file, but it's actually an old one or something. So there's a question that says, would you say this course complements 2804, or is it a step up from 2402 to 2804? I think this is the 2 courses are complementary. So 2804 is really combinatorics and probability. There's some of the things that we'll study in 2804 that actually appear in this course. So there'll be, in 2804, there's often analysis of a couple of randomized algorithms and data structures, a rigorous analysis using the tools from probability theory. And those are data structures that we'll study in this course and maybe analyze heuristically. But they're definitely complementary, right? And they're sort of different topics. This is much more programming and practically focused. 2804, while there's plenty of practical uses for the math that you learn there, the assignments are really math assignments. Is the uploaded code manually checked by TAs? No. The TAs won't be looking at the uploaded code unless there is a question of copying or plagiarism, so an academic offense. In that case, so that all the submissions are run through a tool for detecting this kind of stuff that will tell us if two assignments are too similar to be coincidentally for it just to be a coincidence, in which case TA or myself will look at those things, and if we decide that that is indeed an academic offense, that whole case will be sent to the dean. Okay, so we will, the dinosaur is, one last question. The dinosaur is still at school for another hour. Okay, so last class we looked at array stack, and we did its amortized analysis, which is a really cool proof, and we'll revisit the ideas behind that proof a few times. But it's for the first time you see it, it's kind of maybe feels a bit magic, and maybe feels a little bit heavy if you're not really comfortable with math. Today we'll have a lighter class where I'll really only introduce one trick, but it's a useful one that you can use for the rest of your life. But it should be a fairly light class today with lots of time to do whatever we want. Typically, I would do some demonstrations of the performance of these things during this class, but it's a bit awkward to try and teach on the board and do computer demonstrations at the same time. So class may run a little short today. Okay, so we've seen last class array stack, and that corresponds to Java's array list class. Get and set take constant time because things are stored in an array, but add and remove, they take time that's proportional to n minus I, where I is the position that you're adding and removing from. So it's great if I is equal to n, but not so good when I is small, when I is close to 0. And we've seen linked list, which is neither better nor worse than array stack, because, well, it's worse because get and set, they don't take constant time. So accessing the ith item in a linked list either takes I time or n minus I time, whichever one is smaller, because you don't have direct access to those items. You don't have this just array lookup. You have to walk through the list to get to the item you're looking for. And similarly, add and remove have the same running time, because once you get to the position that you want to add and remove, then it's easy. It only takes constant time, but you still have to get there. So these two runtimes suffer. The bulk of the time comes from the same issue, which is finding the location that you're trying to get to. So position I in the list, which is a different issue than what happens with an array stack. There it's trivial to get to location I, but then you have to move a bunch of things out of the way once you get there. Okay. So the question is, well, can we find something that maybe dominates these, does better than either of these things, beats linked lists and beats array stacks? And that's what we'll do today. And we'll start with a sort of simple, the simplest thing that already illustrates the problem that we have with array stacks. And what I would like to implement is the queue, the FIFO queue interface. This thing's getting very bad. Let me switch to a different color. The first in, first out queue. So we imagine that thing as a sequence. You add things. They go at the, well, just so it corresponds to our picture of a list, let's do it this way. You add things, they go at one end of the queue, and you remove things. You don't say what gets removed. Whatever gets removed is the thing that's been in the queue the longest. Okay. So the first one to enter the queue will be the first one to leave the queue. That's where this FIFO comes from. Okay. And linked lists do great for implementing a queue, but they, if we want to extend that to the full set of list operations, we'll have this problem with get and set. Array stacks, they don't do great with implementing a queue, so array list doesn't do great. And the reason is we have to choose, it doesn't matter what we choose. Either we treat the tail of the queue, where we add things, as the last part of the sort of the end of the array list, in which case it is fast to add. So we can add things to the end of an array list quickly. That's great. But then the remove operation is slow, because we're removing at position 0. Or we can try the other way, adding at position 0 and removing from the last position, position n-1, but that just changes the problem to removing is fast, but adding is slow. So neither of those are a great option. So let's think about how we can do this more efficiently. And let's start by assuming we have some helpful stuff. So in particular, let's imagine a world where we have a really big computer with a really big memory. And if we want to, we can allocate an array whose size is infinite. So let's just pretend for a moment that we have this available to us. We'll see roughly how to simulate it shortly. But for now, let's pretend we have an array whose size is infinite. And okay, so we're going to use this array to implement a queue. And I guess we will store our queue items at consecutive locations in this array. And we'll do something like we'll add here. And we'll remove from here, just to keep the picture the same. So if we think about what this queue needs, there's an array of objects. Let's call that A. And for now, we'll assume it's this infinite array. We have like all of our data structures, there's some number of elements that are stored in the queue. So we might as well keep track of that. And we always use the same name for that. That's n, the number of elements currently stored in the queue. And in addition to that, maybe we should store the location where the queue begins. So in particular, for instance, in this picture, the first element or the next element that we'll remove from the queue, so the location of the head of the queue, it's not at position 0, it's at position 1. And that thing we'll just call J. Okay. So that seems like a reasonable representation, except for the fact that it needs an infinite array. But let's see then how we would implement these two operations, add and remove. So the add operation in this picture, we can even write what the variables values are. We have J is equal to 1, because the head of the queue is at position 1. And n is equal to 1, 2, 3, 4, 5, 6, 7, 8. And now we want to add a new item. That means that we want it to go at this end of the queue. The array is infinitely long, so we know that there's space for it. So let's see how we do that. So this index here is where we want to add it. In this example, it's 9. In general, what is it going to be? Well, it's not index n, right? That would be index 8, and we don't want to overwrite p that is already in the queue. It's at index j plus n, right? J is 1 plus 8 is 9. So we just do something like a at j plus n is equal to x. So that puts x there. And now the number of elements in our queue has just increased, so we increase the value of n. So that's no longer 8, it is 9. Extremely easy. No surprises there at all. All right, and now what about the remove operation? So it's supposed to take something, the head in our queue, and remove it and return it. Okay. So we know that where the thing is that we're going to be returning. It's right here at position j. That's the definition of j, is that it points to the head of the queue. So we save this thing. So now we've saved it because we want to return it. Next, we should probably erase this thing. So it's nice, it's good to be nice to the garbage collector and erase this. So we get rid of it with a at j is equal to null. And then finally, j now is pointing us to an empty array location. That's not what we want. Next time we return something, we want it to be the next thing. So we want to increment j. So now j equals 2. And one last thing we need to do is we have just removed something from the queue. So the value of n has gone down. So we want to decrement that. And then finally, we can return the value that we've removed. Okay, so n drops now from 9 back down to 8. And I guess the only other thing maybe potentially missing from this code is something like bounds checking. So what is the bounds checking that you need to do on queues? Well, there are no indices. None of these take indices as arguments. But of course, there's a problem if you try and remove from an empty queue. So probably you want something in here that's of the form, if n is equal to 0, then do whatever it is you're supposed to do if someone tries to remove from an empty queue. Maybe return null, or maybe throw an exception, whatever it is you're supposed to do. Okay. All right, so that's fantastic. That's how you do adding and removing. That's how you implement a queue if you have an infinite array. All right. That was almost too easy. So let's make life harder and say that instead we want to be able to do not just the 2 queue operations, but all 4 deck operations. And just so you remember what those are we have remove front, first, actually, is the language. First, add first, we have add last, and we have remove last. Okay, good. So we'd like to be able to do those 4 operations now instead of just those 2. All right, so I'll change the name here from queue to deck, or maybe my deck, not to confuse people. Same 3 variables. There's an infinite array A. We'll see a little bit about that in a second. There's an integer n, tells us the number of things in the deck. And there's an integer j, which tells us the position of the first thing in the deck. And already we've done 2 of these things. So the add operation for queues puts things here at the end. So in a deck, that's just called add last. And the remove operation for queues removes things from the front. So in a deck, that's just called remove first. Okay, so we're already half done. Let's do remove last. So I want to take the last item out of the queue. So as usual, since we've seen it already, we should start with the bounds checking. If n is equal to 0, meaning the queue is empty, then do whatever it is you're supposed to do when someone tries to remove from an empty deck. So they try to remove something that's not there. Throw an exception, return null, print an error message, do whatever it is that is supposed to happen. Otherwise, we're actually going to remove this thing. So to remove it, we should save it. Now, at what index, where is the thing that we're removing? Well, we should go to position I, or position J, and then add n, and then subtract 1. All right, so there we've saved it. And maybe, and then we repeat the same sort of processes, same steps as before. We take that location, we set it to null. The value of J doesn't change. We're only fooling around at the end here, not at the front. But the value of n does change. The value of n has decreased by 1. And then finally, we can return the value that we're removing. Okay. And notice there's a little bit of asymmetry here. When we remove from the front, two things have to change. N has to change because we're removing, and J has to change because the front moved. But when you remove from the end, only N has to change. All right. So that's 3 of the 4 operations. Let's do the 4th one. This, I think we can remember. I'll just do it up here. So this is add first. So if we want to add at the front, so in this case, J is 2, we want to add before that. So maybe we should start by decreasing the value of J. And I should change this when I was doing that example. 1, 2, 3, 4, 5, 6, 7. So we'll start by decreasing the value of J. So J drops from 2 to 1. So J is not pointing at B anymore. It's pointing at this empty space. And we can say A at J is equal to X, the value that we're adding. So X goes there. That's great. And then finally, the value that the number of elements has increased. So we should increment the value of n. And that's all we need to do. So there are the implementations of those 4 operations. Does anyone see a problem with these? Does anyone see where one of these would crash or could crash? Okay, so what should be the starting value of j if we're creating a deck? So that's a good point. The implementation is not complete until we say what the constructor looks like. So here's the constructor. We say A is equal to a new array of t things that is infinitely long. We say j is equal to 0 and n is equal to 0. But if you wanted, you could make j be to anything you want because every index is valid. N has to be 0 though, because when we create one of these things, it's empty. Okay, good. So someone suggests that add first is wrong. And once you see this initializer or this constructor, it kind of points to potential real danger, which is if the first operation I do is add first, then look at what add first does. Well, it starts with j equals 0. So it decrements it. So now j is -1, and then it tries to write to array location -1. Not good. That will certainly crash this thing. So there's a problem there. And let's for now pretend that we solve this problem with just a computer that has twice as much memory, because it not only has infinite memory in that direction, but maybe it also has infinite memory in this direction. You can index it with any integer, positive or negative. So in this crazy model of computer, that bug in add first goes away. It's fine for j to be negative, and everything just works. Of course, this isn't anything like a real computer. We'll have to see how to simulate this, because real computers don't have infinite arrays, first of all. And in general, they don't have arrays that you can index with negative numbers. So even if you have a computer with many gigabytes of memory and you allocate an array that's many gigabytes large, that the indices for that array still start at 0. Okay, good. Yeah, so there's some notion of resizing that we're going to have to use because we don't have infinite arrays. And then there's some other notion of, well, that we don't necessarily have to use, but is a handy notion to use. And the thing that we'll use is this idea of modular arithmetic. So you've probably seen this before. Gives us the next best thing to infinite arrays. It gives us circular arrays. So So far I've been, when I draw arrays in this, on the board here, I draw them as this sort of linear structure, a bunch of boxes going off to the left, or going off to the right and off to the left, but usually with a limit on the left, unlike this picture. But here's a sort of different way to draw this, an array. And, you know, the indices you can think of as 0, 1, 2, 3, 4, 6, 7, 9, 10, and so on. And that last index is n minus 1. Okay. So it's not infinite, but it does kind of go off in both directions when I draw it this way, because for any position in this array, there's a position that comes before it, and there's a position that comes after it. So the real problem with add first here was that there was a special position in the array, position 0, that had nothing that came before it. There was no -1, but in the circular array, yes, before 0 there is a position. It's position n-1. And actually, we imagine that we can index these circular arrays using any integers. So this position here has a name 0, just by convention, but it's also the position that appears after n-1, so it has another name, n. And this one here, let me maybe draw those on the outside, n. And this one here has the name 1, but it comes after position n, so it has the name n+1. And this one is n+2, this one is n+3, n+4, n+5, and so on, and then all the way up to 2n-1. Okay. And similarly, we can go the other way around. Starting at 0, if we count backwards, well, before 0 is -1, before -1 is -2, before -2 is -3, before -3 is -4, and so on, all the way back down to -n. So with this circular array, at least we can think of it as I can specify any integer, positive or negative, and it gives me a position in the array. The only issue is you have to be a little careful because there are different integers that give you the same position, like 5 and n+5, or 2n+5, or 3n+5, all refer to the same location. So we'll have to be careful about that. But at least array locations are defined. What is 2n-1? n-1 plus n is 2n-1, which is the same location. So the tool that we use for this is to implement this, and maybe n is not the best thing to use because n is always going to refer to the number of things in the data structure, not the size of the array. So let me just call this m. And what I really mean by m is that is the length of the array. So circular arrays don't really exist in Java, at least, but they're something we can implement, and we can implement them using modular arithmetic. So when I take some value I modulo m, what I get is a number between 0 and m-1. And in particular, the way that you get that number is you take I and you write it in the form I is equal to A times m plus r. And the number that I get is this r. It's in the range 0 through m-1. So if you like, you take I, you divide it by m. You don't care, you do integer division by m, but you don't care about the result of the division. The result of the division would be a. What you care about is the remainder. So this mod operation will take any integer and give you a value between 0 and m-1. And which value do you get? Well, you get the one that comes from uniquely solving this this equation with r between 0 and m minus 1. So you just take away the multiples of m. So that's why here, for example, m plus 1, we take away one multiple of m, and we get back to 1. And here, m plus 5, we take away a multiple of m, we take away one multiple of m, and we get back to 5. And mathematically, this all works fine, even for negative numbers I. So if I did this for I equals minus 2, or sorry, I equals minus 1, then I would get, well, the remainder is going to be something, a number between 0 and m minus 1. So what I would get is a being equal to minus 1, and r being equal to m minus 1. So it would take me to the index minus 1 really would take me to index m minus 1. And it's nice that that works mathematically. Unfortunately, in most programming environments, it doesn't work. Can't reliably do modular arithmetic with negative numbers. So the way we do this in most programming environments is we write it like this, I mod m. So you read this as mod. This does exactly what you expect when I is non-negative and m is positive. But when I is negative, this we need it. Okay. All right. So let's go. Let's go back now and try and make all of this stuff work, all of this deck stuff work with circular arrays instead of this this crazy infinite array. This is, in fact, two-sided infinite array. So let's remember the constructor. The constructor sets A is equal to a new array, and it'll be of length 1. J is equal to 0, n is equal to 0. All right. Good. Now, let's take a look at the remove operations are a bit easier. So let's take a look at those. All right, if n equals 0, then we have some crash. Otherwise, we're still going to be working with more or less the same picture. The difference now is we'll have something like, you know, here's J. It points to some index in our array. And here's J plus 1. That's mod M. J plus 2, mod M, and so on. And that goes all the way up to J plus n minus 1 mod M. So we're going to go with the same model. The stuff in our queue or our deck is at these array locations. This one here, J plus n mod M, is empty. So it looks a lot like this picture, right? Here we had start at j, we go all the way up to j plus n minus 1. And then after that comes an empty 1. So looks very similar. There's just a few things we'll have to look out for now. One is we have to be careful to do modular arithmetic, and the other is we have a finite array here, so we have to deal with the fact that it's finite. So let's start with maybe a remove first, and let's see if this code actually works. Well, J points to the location, the head of the queue that has the thing that we want to remove. So this line of code is fine. Position A at J, we can take the value that we find there and store it. And we can set it to null. Now, this line of code is not great. And the problem with it is it just increments J. And in particular, if J is the length of the array minus 1, and we increment it, it's going to become the length of the array. What we want is for it to actually become 0. Now, the mod operation handles that for us. We just have to be a bit more wordy. We just say J is equal to J plus 1 mod A dot length. The value of n, well, n is supposed to count the number of elements in the deck, so we don't have to worry. We don't need to do mod operations on it. It's a natural number. So we just decrease it because we're removing something from the deck, and then we return this thing. So what does that do here? Well, in this picture, that increases J so that it points to the next element in the circular array, and it decreases n so that this is still true. J increased by 1, which would have pushed these two things ahead by 1, but now we decrease the value of n, which brings them back to where they were before. Could I repeat what we do about mod operations with negative operands? Don't do it. The mod operation with negative operands doesn't do what you want mathematically. And we'll see in the place that where we need it, we'll just do it by hand. We'll implement it ourselves. And worse than that, there's a few programming languages where the mod operation does what it's supposed to. There's other ones where it doesn't, and it's hard to remember which languages do and which don't. I don't know about you, but I program in about 4 different languages fairly regularly, and I just don't want to have to keep track of that. So I just avoid it. And I also have a habit of taking code from one language and porting it to another, which can be the source of serious bugs if the operators don't even mean the same thing in the 2 languages. Okay, so that was remove first. Take something from the front and remove it. No problem there. Remove last. Let's see how that works. Again, if n equals 0, we should throw an exception. This value x, we want to get the value that's there at the last position. It's at position j plus n minus 1 mod m. This code doesn't do that yet, but we can fix it. So we take that index modulo a dot length. So even though we can guarantee that J, we're going to guarantee that J is a valid index without taking mod, J plus N minus 1 in particular is not necessarily a valid index. We have to add the mod operator here. Same issue here. And then the value of N decreases because, right, let's say we're applying this here, then this line sets this to null. We decrease the value of N, so J plus N minus 1 points to there now. And then finally, we return the value of X. Okay. So remove first, then remove last. No problem doing those with a circular array. Add last. Well, let's see what we need to do there. It's only 2 lines, so one of them is easy, right? This A at J plus N, well, we know now we have to take that modulo the length of the array. N plus plus, that still makes sense. We just added something, so we should increase the value of N. Anything missing? Okay, so while I wait for someone to tell me what's missing from this code, I'll answer this question. Why is the last element at position J plus N minus 1? Well, remember, when I count starting from 0 and I count N items, I will only count 0, 1, 2, 3, 4, 5 up to N minus 1. So this is J plus 0, J plus 1, J plus 2, J plus 3, and the last item, the nth item, is J plus N minus 1. And doing that with modular arithmetic doesn't change that. It's when you count from 0 and you count N things, you only count up to N minus 1. Okay, good. So while I was answering that, somebody pointed out what's missing here. Remember, this code originally assumed 2 things. It assumed an array that supported negative indices, which they don't come up here, but it assumed that the array was infinite. And we don't have an infinite array. Now we have an array of some size. Actually, initially, its size is only 1. So we need to do what we always do, or what we've already seen, which is if N is equal to A dot length. So that means the number of items right now, before I add this one, is the same as the length of the array. That means the entire array is full. I'm not going to be able to add anything to it. So if that happens, then I want to resize. And what's resize? Well, resize is exactly the thing that we saw last class, with a slight change to deal with this, this modular arithmetic. But resize will make A dot length equal to 2 times N. Okay. So it's going to do exactly the same thing that we saw last class. When you resize, it's going to, in this case, double the length of the array to give you extra space. And now this next line of code is safe to execute. There definitely is an array location, A at J plus N, mod A dot length, and it's not being used by something else. And then finally, this is also fine. And that leaves us now with only one operation left to do. That's the add first operation. And let me give myself a little bit of space to work. So a few things. This is the original code. This J minus minus is a problem. It was already a problem for us when J was 0. We subtracted 1. We got -1 here. So we need to do modular arithmetic on the value of J. And annoyingly, modular arithmetic doesn't work properly with negative values. So if I take J minus 1 modulo the array length, then I'll get a negative number, maybe -1, which I don't want. So you can cheat that with J equals J is equal to 0, question mark. If true, then A dot length -1. And if not, if J is not equal to 0, that means it's bigger than 0, then it's just J minus 1. So here's a little bit of syntax that goes way back to the C programming language. It's called the choice operator. Maybe you've seen it, maybe you haven't. It's a ternary operator. It takes 3 arguments. The first one is a logical condition. In this case, we test if J equals 0. And if that's true, this thing evaluates to the second argument, A dot length -1. Otherwise, it evaluates to the third argument, J minus 1. Okay? So when J is 0, we have to do this special thing. J is 0. We don't want to give back the answer J minus 1. We want to give the length of the array -1. Otherwise, just J minus 1 is fine. So there's the easy way to do the modular arithmetic in this case. This code is fine. A at J now is a valid index in the array, and this code is also fine. The number of elements has increased. And the only issue left is the one we've already seen. The array might be full, which happens in the case when n is equal to A dot length, in which case we resize. And if that means double the length of the array, now once that's done, you know that there's room for the next element. Yeah, so J minus minus, you don't have to code using modular arithmetic because J minus 1 is somehow easier. If it was J minus a big number, then yeah, you have to actually do some modular arithmetic. In fact, it's a bit annoying. But J, when it's just J minus 1, well, there's only one special case when J equals 0, then you have to do something different. All right. So what do we know here? Or what have we done? Well, I've just showed how to implement all the deck operations using arrays. There's nothing special or magical about this machine anymore. No more infinitely long arrays with 2 ends. Just normal Java arrays that we pretend we've glued the 2 ends together, although they're really just, I mean, that's really just a straight Java array, 0 up to the length of the array -1. And we're just careful about how we do arithmetic so that if we happen to wrap around past the end, we come back to 0. How do we assign it? How do we assign n? The top left corner is a blur. Yeah, it'll be better on the live video, but this is the natural things that we do when adding at the front. It's the same algorithm. We just use modular arithmetic. Sorry if you can't see it on the live stream, but there's nothing weird here. Why is j a dot length minus 1 when j equals 0? Well, it's not j that's equal to a dot length minus 1. It's the result of j minus minus, the result of subtracting 1 from j. So 0 minus 1, of course, is minus 1. But in the modular arithmetic world, minus 1 is actually m minus 1, the length of the array. But don't even think about that too much. Just think, if I'm walking in this array and I was at position 0 and I take a step backwards, I should wrap around to the end. Yeah. All right. And I think it's easy to see. Well, here there's only a few lines of code. So that definitely runs in constant time. There's no looping. There's nothing that takes any variable amount of time. Same thing here. So that runs in constant time. Here, except for the resizing, there's only 2 other lines of code. So those run in constant time, except for resize. And the same thing at the top here, that runs in constant time, except for resize. Now, the nice thing is we don't have to analyze resize again because we did that already for array stacks. We saw that this resizing operation, where when you need to grow the array, you make it twice as big and you copy everything over. We saw that if you do m operations, the total time you spend resizing is only proportional to m. So we think of that as meaning on average, or the time per operation is only constant. So it's not true for every operation, but if I amortize it over all of the operations that I do, then you only spend an average of a constant time resizing per operation. Okay, good. So now we have the lesson in hand, but what I would like to do is go back to what I promised at the beginning, which was something that is better than linked lists and better than array stack. So remember that table had array stack. We have constant time for get and set. And we have 1 plus n minus I for add and remove at position I. Linked list. Slower for get and set, but faster in general for add and remove. So in a linked list, adding and removing is fast when I is small or n minus I is small. In an array stack, it's only fast when n minus I is small. So meaning you can add and remove at either end very quickly in a linked list, but not in an array stack. So let's look at what the textbook calls array deck. This is not the Java collections framework array deck. This is what's described in the textbook. The Java collections framework array deck is basically what we just did here. It only supports the deck operations: push, add first, remove first, add last, remove last, and some other names for those operations with slightly different semantics. But that's basically how the array deck class in the Java collections framework is implemented, is what we just did. But this thing here from the textbook, it implements the list interface. So get and set and add remove. And the name, why is it called an array deck then? The name is just to remind you that it will be fast if you add and remove only at the ends. Okay. And the running times look like this. So it uses an array, so get and set will take constant time. And add and remove they'll be as fast as the linked list. So that's in general faster than array stack for small values of I, and at least as fast as the linked list. But get and set are faster than the linked list and as fast as the array stack. So this one dominates those two structures if all you care about is the performance of those four operations. Okay. And the structure is basically what we've seen. The nice thing is somehow the operations are even simpler. Try and stay out of the top corner if I can. There's an array, A, there's an integer, J, there's an integer, N. When you initialize one of these things, it's exactly what you expect. A is equal to a new array of length 1. J is equal to 0. N is equal to 0. All right. The get operation. So look at this picture. At any point in time, we'll have J, which is the list item with index 0. So the array itself, the Java array, is just indexed like normal. But to know what the list item 0 is, well, it's going to be stored at position J. So here's an example where J equals 4 and N equals 1, 2, 3, 4, 5, 6, 7, 8. So this last item of the list is J plus N minus 1 mod the length of the array. So 4 plus 4 plus 8 minus 1 is 12 minus 1 is 11. Mod the length of the array. This is an array of length 11, so it's at position 0. All right. So then the get operation is really easy. We just ignore bounds checking because we already know what that looks like. You just return. Well, if I want list item J, then I should go to position, I'm sorry, list item I, then I should go to position J plus I, mod the length of the array. Where is list item 0? It's at position J plus 0. Right, J is 4, list item 0 is at position 4. Where is a list item 3? It's at position J plus 3, mod the length of the array, but that doesn't do anything because it's smaller. Where is a list item 7? It's at position 4 plus 7 is 11. Mod the length of the array. Here at position 0. Okay. And set IX, that's also trivial. So we save the value at position I, so we get it. At list index I, we change the value to be this new value X, and then we return the old value. That's what set is supposed to do. Okay. So that only leaves the add and remove operations. So what we're aiming for, so these definitely run in constant time, right? These are just straight line code, a little bit of arithmetic and returning a value in an array. So that's definitely constant time. What we're aiming for with these operations is to run in time that's the smaller of these two values, I and n minus I. And why is that, or what's the point of that? Well, how are we going to do that? So let's forget or not worry about the modular arithmetic for now. But if I have a big list with a lot of items in it, and I say, well, why don't you add something right here? So then I can't get around the fact that I'm going to have to move some data out of the way. And what is it that I will have to move? Well, I have two options. Either I can take all this stuff and push it to the right one position, or I can take this thing and move it to the left one position. That will free up the spot that I need to put this new value X in between the two existing values. So the new value X will be at the new list position 1. So in between the old values, list item 0 and list item 1. And so there's two options. I can push everything to the right, or I can pull things to the front. In this case, I think it's pretty clear what to do. Right? I can just move this item one position over, and that gives me a space to put X. Similarly, if I was going to add over here, the options are to take one item and move it one position to the right, or to take n minus 1 items and move them one position to the left. it's faster for me to move the one item. So, what's the code for that look like? Well, it looks like this. If n is equal to a.length, and resize, that's good. So at this point, we know there's room to add the thing that we want to add. And so now we just want to do something like if I is less than n over 2, so that means I is in the first half of the list, then I think it makes sense to take everything that comes before I and push it to the left. So we're going to shift things to the left. And otherwise, we're going to shift things to the right. So what does shifting things to the left look like? I'll have to do this quickly, and I'll for sure make a mistake. But it's just a for loop that does something like, let's say, j is equal to, I have to do this, this minus thing. So pushing things to the left means, if this was the value of j, I need to move it 1 to the left, which means I need to subtract 1 from it. And I have to do that using modular arithmetic. So that would be a.length minus 1, in the case j equals 0, or just j minus 1. Otherwise, then there's a for loop for, let's say, k is equal to 0, k is less than I, k plus plus. And what do you do inside that for loop? You take array position A at j plus k mod the length, and you set it to array position A at j plus k plus 1 mod the length. Yep. So if I did that correctly, that corresponds to shifting everything before list index I to the left by 1 position. And that's, if I is smaller than n over 2, that means the minimum here between I and n minus I is actually I. So that's how much work you do there. Otherwise, you have to shift things to the right. And so that's going to look something like, for integer k is equal to I. I don't know. You have to count backwards. K is equal to n. K is bigger than I. K minus minus. And that looks like A at j plus k mod a.length is equal to A at j plus k minus 1 mod a.length. And this is the code for shifting everything from position I onwards to the right by 1 position. And this only happens when I is bigger than or equal to n over 2, in which case n minus I is smaller than I. And then finally, you wrap up with A at j plus I mod a.length equals x and n plus plus. So I know that that's quick, but I think that the idea is fairly straightforward. You make a decision whether it's more efficient to move I things or I minus 1 things to the left, so move them back, or whether it makes more sense to move them to the right. And I guess actually in this case, when this finishes, oh no, it already lowered the value of j. Okay, good. So yeah, I think that's more or less correct. Of course, you can look in the textbook for the exact code, but it has roughly these steps. And that gives you this running time for the add operation. And the remove operation, I think you guys can see where this is going. When you tell me to remove something from the list, maybe remove this thing, something has to come and fill in the gap that's left from the thing that you remove. You have choices for that. You can take elements at position 0 through I minus 1 and move them to the right to fill it in, or you can take elements at positions I plus 1 up to n minus 1 and move them to the left. Again, which one of those two things you should do depends on whether I is less than n over 2 or bigger than n over 2. Okay, so yeah, so that's it for the lesson today. The lesson today is really about using modular arithmetic to get these circular arrays. And sort of the bigger lesson, or the sort of other lesson, is already we're learning techniques that we're getting to reuse over and over, right? Because last class we were struggling with an array stack, and what we were struggling with was the fact that arrays have a fixed size when you allocate them, and they don't grow or shrink. Here, we got that behind us last class. We analyzed it. Mostly, hopefully many of you understood the analysis. And now we don't have to worry about it anymore because we have a technique for dealing with that. And that technique works for any of these array-based structures. It's just this resizing operation that makes the array twice as big as necessary for the current size. So we got that out of the way. We didn't have to worry about it anymore, which is why it made sense to think about infinite arrays, because don't worry, they'll grow when we need them to. And now the next technique, the sort of new trick here, is just using modular arithmetic to simulate arrays that are circular. All right, so that's it for today. I'll scan for questions, but feel free to ask me another question. Okay, so should we be checking to see if it's centered in the array before shifting? I know it's possible we favor one side more than another. No, because this picture here, remember, this is still in a circular array. And all of the shifting that we did when we did this, we're using modular arithmetic here. So really, there is no one side or the other of the array. I mean, maybe a more accurate picture would be this. There's our array. There's the stuff in the array. Someone asks us to add or remove at some position I, and we have to decide, in the case of adding, we have to decide whether it makes more sense to take these two things and move them this way, or whether it makes sense to take all these things and move them that way. So there's not really a notion of left or right in the center of the array, because the array is circular. Dave Z's question. Yeah. Yeah, so there's no balancing. balance here is just if it gets oversized. And in the remove method, we would also have a thing at the end that says if the array is more than 3 times the number of elements, we can resize to make it smaller. Yeah. So are all the arrays circular? The way we're written the code here using modular arithmetic on the array indices makes them circular. So it makes them behave like circular arrays. If you have questions about the submission server showing compilation errors, then you should see someone during their office hours. We have lots and lots of office hours. Wouldn't centering change the time to access elements with get? Well, no, because get is just you just do a simple arithmetic operation, and well, this should be a at I, and just go directly to that array location and return it. So get runs in constant time. Okay. Not sure what happened on the night of the 19th. I'll check on the server to see that there's sufficient disk space. And no, you don't run into compilation errors if your code takes too long. The code takes too long comes at the testing phase. Yes, Ujan, in the resize operation, feel free to look at the chapter in the textbook. It looks a lot like this, except that just before it returns, it checks if the length of the array is more than 3 times n. And if so, it resizes so that the length of the array then is only 2 times n. When does it resize in the if statement? Here, if the length of the array is equal to n, meaning if the array is completely full, we have to resize because we're not going to have any space to put the new element that we're adding. No, there's never an issue of it taking too long to compile. So the code you submit to the server, the time it takes to compile it is not timed. That's not an issue. Too long to run is when the server will stop it. So here you're asking, when does it resize in the add ix statement? That's it. The condition is if the length of the array is equal to the value of n. So the array is completely full, then it resizes. Will you study how to build a server in the future? Not in this course, maybe in some internet programming course. Should we not add resize to remove to be space efficient? Yes, the remove operation in general should have resize in it to make sure the array doesn't stay enormous after removing a lot of things. I would say that you should have that in the remove operation. And if you look at the implementation in the textbook of this class, there is a resize in the remove operation. One thing I can tell you, though, is if you look, or you don't even have to look at the implementation, you can just run it of the Java's array list class. It does not resize on remove. So if you create a Java array list and you add 1 billion elements to it, and then you remove them all, you're left with an array of length at least 1 billion, as long as you keep that array list around. Yes, it resizes when the array is full. The assumption at the beginning of an infinite array was just to make lives easier for us. Well, we saw how these things can work in an ideal world, and then we saw how to implement all those ideal things. Infinite arrays, we get those by using resizing. Circular arrays or arrays with negative indices, we get those using modular arithmetic. Okay. All right, that's it for today. Thanks for showing up.